So I'd like to introduce you to our guest speaker tonight. Tom DiLiberto is a meteorologist with the Climate Prediction Center with the National Oceanic and Atmospheric Administration. He has a bachelor's degree in atmospheric science and a master's in meteorology, and he's known for kind of breaking down complex concepts for the non-scientist. So we are looking forward to learning from Tom tonight. So welcome.
Hi, thank you. Sorry, I'm having a little sound issues. I think everything is good now. I can hear all of you. You can all hear me. It's wonderful. But hi, everybody. So yes, I'm Tom DiLiberto. I'm a meteorologist, climatologist, climate scientist. I always say it depends on what question's being asked of me at that exact moment, and I end up being that person. And I'm excited to talk to you all today a little bit about snow. And I'm going to talk about, I have some slides, and we'll have plenty of time for questions. Since I know winter weather is probably very exciting for all of you and interesting to all of you. It's very much interesting to me. I grew up in New York, on Long Island. So most of my childhood when I was a kid was spent hoping for a big nor'easter to leave me with a foot and a half of snow so I wouldn't have to go to school. And honestly, it's partly part of the reason why I became a meteorologist. So let me share my screen and
Tom,
we'll talk about.
I'm gonna turn up just Tom, I'm gonna turn off my camera now and I'll come back at the end and we'll go through the questions and I'll kind of facilitate that kind of Q&A with you at the very end, okay?
Perfect. That's great.
Okay.
Thank you. Snow. Let's talk about snow. I got some slides. I might go through some of them fast because a lot of them are just pretty pictures. But we'll talk about snow today. So first, that's me when I was 4. And I'm the youngest of 3 boys. Bless my parents. And I love snow. Snow is probably my favorite thing in the world. Um, Usually when you meet a meteorologist, meteorologists tend to have um, like certain aspects of weather they like more than others. Like there are hurricane people and tornado people. I'm a snowstorm person. I like nor'easters. I like lake effect snow. I just like snow. So who better to talk about the science of snow than me? Someone who knew I wanted to be a meteorologist since I was in 3rd grade. And I was talking a little bit earlier. Part of the reason of that is because I always like being able to tell my friends when there might be a snow day. I like being that person who had the info on the forecast. I also hate suspense, so I kind of like knowing what was going to come to me. So we're talking about this. Is that a pretty snowflake? This was created in a lab. Isn't that neat? These are all lab created snow crystals, but these are all shapes that snowflakes can be in. They're gorgeous. I always love the fact that our Earth can do such amazingly beautiful things, and just like naturally, right? And this is just a natural thing. These are other lab grown snow crystals that you can see all the different shapes and sizes and the way they look. All of these are literally just ice crystals. And it's just an amazing thing to think about, that snow, that stuff that falls from the sky sometimes. I'll get into that later. Can lead to so many different potential shapes and colors and sizes and whatever you want to call it. But these also look like this in nature too. These now, this is my advisor back in grad school. I won't say how long ago that was. But these are actually images he took, I believe, like 10 years ago, in a snowstorm on Long Island. And these are actual snowflakes. These are from the sky. They're from Mother Nature. You had those perfect ones we saw earlier created a lab setting, but you can see here that, yeah, that's what they look like. Granted, they're a little bit uglier. They've been beaten up a bit as they fall from the sky, but these are what snowflakes look like in real life, and it's amazing to think about. Now, you may have heard the statement said before that there are no 2 snowflakes are alike, and that is true, and I'll get into that in a little bit. But I don't think people fully appreciate how different snowflakes can look. And the reason for that is because it depends on not only the temperature of the atmosphere at which not only the snowflake forms in, but travels through, as well as how much moisture is in the air. There's 100% relative humidity. It's as much moisture as the air can hold as possible. You can actually have, it's crazy to think about, something called super saturation, which is more than 100%, mean, the atmosphere is actually holding more moisture than it should be able to hold. It just needs something to basically take that moisture out. And depending on where you are in the atmosphere, you can get all of these different designs of snowflakes. You get your classic dendrites, your six-sided things, these beautiful things. You can get things known as hollow columns. You can get thin plates that look like basically hexagonal shapes. You can get something called needles. Those right there, they look exactly like that. They're needles. And if you've ever experienced needles falling from the sky, it is mind-blowing because you feel like, oh, this should be crazy. And then all of a sudden, these like thin little tubes just fall from the sky. And you can see them on your coat, on your jacket, in your hair, and your hands. And all of these are normal. Now, why they do this, why they go into different shapes, I don't think exactly why cause certain shapes is exactly known, but the idea here is that it's all based on the molecular structure of water as it freezes. Right, H2O, right, 2 hydrogen, 1 oxygen. The reason why there are actually 6 sides on a dendrite we classically see is because a water molecule actually has about a 120-degree angle between those 2 hydrogens and the oxygen. That's consistent. So when it freezes and it attaches to something in the middle, you end up getting that sort of that angle. And when you put that into a crystal form, it gives you 6 sides. And that's why you tend to see 6 sides. That's why you always see. If you ever see a snowflake with 8 sides, it's not like a 4-leaf clover. You can't have that. It's not molecularly possible to get that sort of thing. So let's get into how snow actually forms. So what are clouds made up of, right? That's where they come from. Well, clouds are made up of water in all 3 phases: solid water, ice; liquid water, those stuff we drink; and gas, water vapor. That's all what's made. Now, what you're looking at when you see a cloud is actually solid water. It's a tiny itty bitty molecular, tiny itty bitty, tiny raindrops, basically, are cloud particles that are liquid water attached to some sort of what we call nuclei, or something that's like a piece of dust, like really small. But that's what you're seeing when you see a cloud. But there's gas involved in that as well. And then within the cloud too, there's also snow crystals if it's ice crystals if it's cold enough. So let's get into how a cloud forms. Well, clouds form if there's rising motion in the atmosphere. Basically, you take air, you move it up. It gets colder as you move up in the troposphere. When you cool air down, it can hold less moisture in it. So at some point when you cool that air, you cool it enough so that it's completely saturated with moisture. It holds as much moisture as it possibly can. And that's when you start condensing all that gas, water vapor into liquid, and you get clouds and you get snow. You get clouds. If now you have enough rising motion, you have enough water in that cloud, you could actually create a process which then leads to there being snow and water, rain droplets developing. And it's a lot, by the way. You need like millions of like nuclei to clash together to form a rain droplet that's heavy enough to fall due to gravity. Otherwise, it's kind of like chilling in the air. Same thing with snowflakes. So here is a thing to think about: a cloud droplet and a small rain droplet. If you times this image here by 2, that's the difference in size between what a cloud droplet is and a small rain droplet is. So we're talking a huge sense of scale here. So in order to create a snowflake, you basically need temperatures to be below freezing. You need a nuclei, which I mentioned previously is like a piece of dust. And you need something called supercooled water, basically water that's below freezing but still in the liquid form because it needs something to freeze onto. So that liquid, that super cool liquid water droplet, it's liquid, but it's below freezing. It just is waiting for somebody to reach out so it can freeze onto. I say super cool rain droplets are very clingy, right? They just need something to form onto. So when you take that liquid water that's below freezing, you combine it with that something that can stick onto that nuclei, you get yourself a developing snow crystal or an ice crystal. So how does an ice crystal grow into a snowflake in order to fall to the ground? Well, it grows at the expense of liquid water droplets in a cloud. So you can see here all those molecules around the snowflake and around the water droplet. You can't see it because it's happening in a cloud, so it's really, really tiny. But also, like, around the liquid water droplet and around even a snowflake, you have water transferring between phases. So you have it going from liquid to, to gas and vice versa. So it's you end up seeing more molecules. We see vapor around the raindrop, or at least the cloud nuclei, that sort of liquid water, and then you have less over the snowflake. And what that does is it creates a pressure difference. There's higher pressure over the raindrop. There's lower pressure by the snowflake. And if we know anything from weather, right? Air moves from high to low. Why does air move from high to low? Because atmosphere is trying to make everything equal. It's kind of a very poetic thing that our atmosphere is always trying to make things equal, always failing, but always trying to do that. And it's trying to make things equal. So if things are equal, higher pressure on the raindrop of the liquid water than it is on a snow crystal, and lower, and there's a difference there. Well, those molecules end up moving towards the snow crystal, and it grows at the expense of the liquid water droplet. And eventually, droplet disappears, and you end up getting these snow crystals growing. Now, the interesting thing about this process, this Bergeron-Findeisen process, is that one of the scientists who was involved in this process, Alfred Wegener, is also known for something else. And it's a crazy thing that one person can be involved in something so fundamental in atmospheric sciences, but also plate tectonics. This is the guy who did plate tectonics. So if you've ever felt like you've never felt lazier than realizing this guy came up with two things that are mind-blowing. But just a little fact for everyone to think about. So again, getting back to this image again, the reason why no two snow crystals are alike is because that process of taking water vapor and freezing it, or even like onto an ice crystal, depends on the temperature, depends on the humidity, how much moisture is in the air, as well as where it falls to. Now, if you've ever seen a snowflake fall, it doesn't fall necessarily straight, it kind of wafts. There are micro scale differences in the temperature and in the humidity within a cloud. So as a snow crystal is falling, it's going into different temperatures compared to a snowflake that's near it. No two snowflakes take the same path through a storm. Because they don't take the same path, they don't look alike. You can go from something that looks like a sectored plate there in the middle to something that looks like one of those images at the very top that looks like a thin plate. And you can see that literally in the snowflake. And what you're seeing within the shape of the snowflake is basically a story of the temperature and humidity of the cloud in which that snowflake formed. And you can see these kind of interesting sorts of features. Here's some more classic images from microscope done in a lab setting, so you can see how pretty they are. Stellar crystals, needles are up there on the top. It's fascinating. Those are what hollow columns look like, and those sector plates. But again, depending on how the snowflake falls, you can see these things sort of combine themselves. You can see here additional ones. Those are columns with a plate into a hollow column with plates attached to them. The bottom one is like a sector plate snowflake that has ice literally on it, like it's rimed ice, basically. It ran into water droplets that froze on it, like encasing this ice crystal in ice. So it's called rimed ice. It looks like it's an adolescent, that looks like an adolescent snowflake with pop marked from acne, but it's just ice, frozen onto the actual ice crystals, the snow. So that was a lot of information about snowflakes. I think it's really, really neat. One question we always get is, why is snow white? Well, one, light goes into it and gets reflected back out, so our eyes see that as white, which is the reason why snow is white. Another question also comes up: how can snow be light, and then how can snow be heavy? Right? You've ever tried to shovel powdery snow? You're like, oh, this is great. You ever tried to shovel that heavy, wet snow, and you're like, oh, my back, or you break a shovel? Why is it like that? Well, it's the water content in the snow. The drier an atmosphere is, the less water it can hold, but it can still cause snow. So if you have a cold atmosphere creating snow, it tends to have less total moisture, total water in it than if a snowdrop, let's say it started snowing and it was like around 32 degrees. 15-degree snow has less water in it than 32-degree snow because just of the atmosphere in which it was created and what it exists in. So, if you take, let's say, a ton of snow and you melt it into liquid water, you may not actually see a lot of liquid water in snow that was formed in the colder temperatures versus one that came from a big snowstorm. I'll get into the lake effect snow is a really, really good example of that. You could have 6 feet of snow falling in lake effect snow. We just saw that in Buffalo a couple of weeks ago. And there's actually not a ton of moisture in that snow. You think, oh my gosh, it's probably like what, like 6 feet of snow. It's like probably at least like a foot of liquid water. It's probably not. It might be 1 inch is equivalent to like up to sometimes 50 inches of snow versus a really heavy wet snow can be 1 inch of liquid water is equivalent to around 10 to 12 inches of snow. So it really depends on the temperature and the type of storm that it's all falling into. So let's talk about that. This is just one of my favorite images. I love images when you can just see from space. You can see the snow on the ground. You can see all the topography associated with it. So let's talk about that. What are some types of snows that affect the Great Lakes? One, you may have heard of these before, the Alberta Clipper. It's exactly what it sounds like. It basically comes from around Alberta in Canada. It moves really, really quick over to the east, and it drops light snow. I call it conversational snow. It's pretty snow. You're looking at several inches. It makes it so you can't see the ground. It might, depending on the temperatures, it might coat the pavement. These are quick moving storms. And they're kind of, your classic little things that can kind of occur. Now, the one that people most likely talk to, at least for me on the East Coast, your nor'easter, right? These are those giant storms that come up the East Coast. They take advantage of the warm Gulf Stream and they basically sock the Northeast in some shape or form. Someone usually gets a lot of snow. Someone gets really upset by getting rain. And somewhere in the middle, someone gets upset because they didn't get as much snow as they wanted to. And the classic thing with this is that rain snow line usually sets up a long I-95. So it stretches from Washington, D.C. to Baltimore to Philadelphia to New York City. And it's classic. It's very, very hard. The difference of 15 to 20 miles can mean the difference between 3 inches of snow and a foot and a half. We've seen it plenty in the last 10 years or so. Those sorts of things happen. And the reason why we can see these things start to form, and this is also true for the Great Lakes, is that we get a wavy jet stream. A jet stream is an area of fast moving winds, 30, 40,000 feet in the atmosphere. Think of it like a storm highway, but when it gets kinky like the kinks like this, it's really wavy. It allows cold air to sink in and warm air to push north. And in between those two things is where you get that motion, that counterclockwise flow, and you end up seeing a storm kind of ride along the bottom of that. And it helps basically take advantage. Storms like this, like nor'easters and storms that kind of affect the Great Lakes, they are driven by temperature differences. So the colder the air, the warmer the air near each other leads to there being stronger storms in a general sense. So it's a story of cold versus warm. And it's more complex than that, but for the general speaking, that's what we're looking at. And that's why we can kind of see those sorts of things that have happened. So for the Great Lakes specifically, when you get a lot of snow, let's take a look at what are the normal sorts of tracks of snowstorms that give you all the best snowstorms. By best, I mean the most snowstorms. That may be biased by my part, but give you the most snow. So that Alberta Clipper I showed you earlier, if you want to look for the biggest snowstorms for the Great Lakes, you're looking at types 2 and types 4. You can see type 2 kind of starts in the panhandle of Texas and Oklahoma, kind of turns up and then moves up into the Great Lakes. Type 4 kind of transects from the other side of the Rockies and then kind of moves to the south. Now, it can usually, depending on that track, it can move just far enough north, it can really sock the Great Lakes. And then 2 is a classic one. I think most of the storms you could think of for the Great Lakes in history, they all have crazy names like the Cleveland Super Bomb and other things like that, kind of came from this type 2 storm. And again, associated with a wavy jet stream, just not over the East Coast, but smack dab there near the Great Lakes. And at least these storms moving up that area and just getting incredibly strong and bringing so much moisture in from the tropics and the Gulf of Mexico all the way up into the Great Lakes and turning that into snow. And within snowstorms, you can have things called snow bands. So you can have this giant snowstorm, which is it's dropping like, let's say, a foot of snow, but someone always gets like 24 inches of snow. And you're like, how did that happen? Well, usually what happens is one of these sets up, a snow band. This is kind of like inside the storm itself. There can be areas what we call convergence. So low level convergence. So basically places where the winds are hitting each other more, leading to there being localized areas of faster air moving up. Basically think it is like there's parts of the storm that are better at making snow than other parts of the storm. And usually usually in all strong storms, you get these bands to set up. And depending on how the storm is moving, sometimes the storm moves and then moves in a different way, like it moves kind of like to the north and then it moves to the northeast. Well, as the storm is shifting like that, usually some place or another gets stuck on the pivot point of these storms under this snow band, which could be dropping 3, 4 inches of snow per hour. You could see less than a fourth of a mile. These are the heavy, heavy, heavy snow bands. So that's usually where you see the jackpot totals during snowstorms. It's where these bands end up setting. And I'm talking about really, really heavy snowfall, so I feel like I'd be remiss if I don't talk about blizzards, right? Are all the things I talked about blizzards? No, blizzards have a specific definition. It involves the winds being a certain speed, how long the winds last in that speed, how much visibility you have, and the fact that snow exists in any shape or form, on the ground or in the air. So basically, blizzards are just saying that the winds are, I think, blowing over 35 miles an hour for what's it, 6 hours combined. And then you can't see for more than a fourth of a mile for the exact same period of time. Blizzard, by definitions, have nothing to do how much snow falls. Nothing to do with it. It's purely a wind and visibility thing. We've seen what's called ground blizzards across the Midwest and the plains before, where they've had snowfall the week previously. A storm comes through, blows that storm up, blows the wind up, so you can't see anything, and you reach blizzard conditions without snow necessarily falling from a cloud or a storm. So blizzard, again, we talk about it like they usually associate, but there's nothing in a definition of a blizzard that says a blizzard only happens if you get more than 12 inches of snow. There's no definition like that when a blizzard is being discussed. So I'll take another thing that's kind of classic to the Great Lakes. I think globally speaking, the Great Lakes are the experts and kings and queens and the royalty when it comes to this, which is lake effect snow. Lake effect snow is these basically streamers, these lines of snow or precipitation that form off the lakes, and they push into areas downstream on the other, so usually on the eastern sides of the lakes. These lines of clouds and storms can be hundreds of miles long. This is an image taken, I believe, from 2017, I think. But this happens every single year. And you can see intense lake effect snow. This is this is 2014. This is one of the epic snow events in Buffalo in the last 10 years. Granted, they just had another one a couple of weeks ago. That is a snow band. This is radar. This is precipitation falling scale of 5, 6, 7 inches an hour, not moving, consistently forming over and over again. And if you're wondering, wow, that really looks like a really straight line at the north end, is that actually really what it looks like? Take a look at this. That is that snow band. No snow is falling where this person with his camera is. Underneath that snow band, you can't see the hand in front of your face. Inside that snow band, you're seeing the snow measured in feet. And this is a classic thing that forms downwind of the Great Lakes. This is the same time in that event, that 2014 event, but you can see lake effect snow coming off of pretty much every Great Lake. So how does lake effect snow? Well, lake effect snow basically needs there to be cold air blowing over relatively warm water. As long as you have a certain difference between the water temperature of the lakes and the cold air blowing above it, basically what ends up happening is that cold air, the difference between those two, leads to there being moisture being sucked up from that warm lake. It gets funneled basically into one single snow band and then pushed down the lake. So usually we'll see a storm kind of moves through. On the back end, you get cold air blowing from the west, from the northwest, from the westerly direction over ice-free, warmer, generally warmer than average lakes. Usually this happens in the beginning of winter. This happens in November. You can see it in December and January too, if there's not ice-covered lakes, and you get snow to form. It's literally just as simple as this. Now you're thinking, can this only form along the Great Lakes? No, we've seen this phenomenon occur in the Great Salt Lake. I went to school in upstate New York, in the Finger Lakes, if you know what those are. They're really, really narrow, and you can see lake effect snow off the Finger Lakes as long as the wind is coming from a very specific direction. Like literally, if it's 5 to 10 degrees off in the 360 scale in a circle, you can see it. It's pretty remarkable. And this is just a thing that's really, really fascinating when it comes to specifically winter in the Great Lakes. So let's talk about the current winter in the Great Lakes. You guys may know this. It's been pretty warmer than average. This is taking a look at the temperature average in the United States, November and December. We're 1 day away from getting the January numbers up. I wish I could have gotten that for you, but I'll show you the next slide. January looks just as warm. And we've seen warmer than average temperatures across the entire country, but especially around the Great Lakes, getting into the northern plains. And this is what the temperatures look like specifically for January 1st through the 30th of this year. Again, temperatures consistently above average in this area. What has that meant? Well, looking at the snowfall totals, this is the total snowfall analysis from the end of September to now for the United States. And you can see you've seen around 1 foot to 2 feet of snow. Some areas seeing 2 to 3 feet of snow. Probably slightly below, probably below average in total, but you can see that just south of that, in the southern parts of Illinois and Indiana and getting into Ohio, that's a snow hole. And again, the Northeast really has not seen that much either, as well. In fact, if we take a look at the at least the last month, for snowfall, for the Great Lakes, that's the right image. That's percent of mean. So basically, anything that is in the greens or blues, you're seeing above average, and anything in the oranges and yellows, you're seeing below average. And you can see in the last month, you pretty much had one storm probably comes. You can see the storm track, right? That one system or a couple systems creating an individual track, leading to there being a stretch of area seeing above average snowfall, while you're seeing below average to the north and below average to the south. Now, often when we get asked by folks about like, why are we getting less snow? Maybe just there hasn't been a lot of storms. Well, the image on the left can tell you the real story. That's just the precipitation anomaly. So you can see those areas in Illinois and Indiana and Ohio. Precipitation-wise, they've seen an above average amount of precipitation at the exact same time they've seen a below average amount of snowfall. The only reason for that, it's too warm for it to snow. All that precipitation is now falling as rain. Meanwhile, if you look further to the north, in Minnesota and northern Wisconsin, you have below average precipitation and below average snowfall. So there you can say it just has not been precipitating as much. So there's a lot to be said here in terms of the types of winters that we've been seeing around the Great Lakes, that there is no one single story. In this image itself here, we have 3 separate stories going on. A narrow area seeing snowfall, 2 areas not seeing snowfall, but for 2 different reasons. So it's a interesting sort of way of looking at it. And this is true even for the Northeast. I live in Washington, D.C. We received our first inch of snowfall in 2 years a couple of weeks ago. So I think we saw like 4 inches total. And we've actually seen above average precipitation for the last 2 years during that exact same stretch. It's been very, very wet. It's just been too warm for it to snow. And you can see here, this is taking a look at a winter severity index that was created by the Midwestern Regional Climate Center. This is basically taking into account all the storms that you've seen so far, everything else that you associate with severe winter weather. I don't like the color scheme on this because red seems bad to me with these sorts of things, but red here is mild, and look at all those reds around the Great Lakes. So even in places you've seen above average snowfall, it's been a pretty mild winter so far. It has not been a particularly bad winter. And that is true for a lot of areas across the north central and the northeast United States. Another thing we can talk about is also directly associated with lake effect snow is how are the Great Lakes doing? This is taking a look at the average ice cover across the Great Lakes. The red line is the average. The black line is what this year has looked like, and all the other lines are past years from 1973 to 2023. You may note that on that bottom, did it take 2024? Did it take, this is go back into 2023, it's basically this year. Man, did it take a lot of time for the lakes to even begin to ice over? Again, it was so much warmer than average across the Great Lakes. We saw it spike getting up closer to what you'd expect it to be, and then all of a sudden it went back down again. It got warm again. So this has led to very, very low ice coverage around the Great Lakes, under 10%, when on average they should be seeing nearly 30% of the Great Lakes. So what does that look like? This is what the Great Lakes ice cover looks like as of January 30th. Those areas in basically the areas that you see that are not in blue have ice in them. You may note that they're in kind of protected bays, shallower bays. They're in shallower areas. They're not covering the entire lakes. Now, a lot of these lakes aren't going to freeze over entirely. Lake Erie is generally the one that freezes over because it's the shallowest of the lakes. And you can even see there that is nowhere close to freezing over. And lake effect snow can continue pretty much as long as the lakes are ice free. So you can actually see lake effect snow longer than you'd normally see it because it's been so warm. So you just need some cold air to come on across it, and you can see lake effect snow. But this has been a heck of a story so far this winter, is how warm it's been across the Great Lakes and how little ice coverage there's been pretty much across the board. What's the forecast look like? Well, this is what the monthly forecast looks like for February. This was issued today. Today's the 31st? Yes, today. This was literally issued today. So sadly, February looks like a continuation of what we saw in January and what we saw in November and what we saw in December. Warmer than average temperatures across the northern tier of the United States into the Great Lakes. And on the flip side, it looks like there's odds here for it to be below average in precipitation as well. Warmer than average, drier than average. Am I saying it will not snow in February? Absolutely not. You can still get storms. These are improbabilities. These are not guarantees. So this is a slight tilt in the odds towards it being drier than average and a little bit more of a signal for it being warmer than average. But that is by no means a guarantee. This is just what the trend is. And this image, a lot of this, the way this looks is due to El Nino, which is what we're currently under. El Nino tends to lead to there being warmer than average conditions across the northern tier of the United States, wetter than average conditions across the southern tier of the United States. The storms are tracking further south, they're not tracking further north, and below average precipitation where they normally track, which is across the Great Lakes. So this is a pretty normal pattern you'd see for this exact year, but you can very well still get snow with this, although this is not a signal you'd want. If you want lots of snow, you would not want an El Nino, and you would not want a forecast like this. So let me end this with talking about climate change. This also gets brought up a lot. How is climate change affecting snow? How is climate change affecting the Great Lakes? Well, I have some interesting things to talk about. Lake effect snow actually might increase for a time being as the world warms. Why? Well, lake effect snow relies on ice-free lakes. If you keep the lakes ice-free longer, you extend the lake effect snow season, which means you can get more lake effect snow as long as it's cold enough to snow. At some point, the temperatures will warm up more enough to the point where you won't get lake effect snow. You'll actually get lake effect rain. So at least for the time being, you actually might see more lake effect snow. We've seen that generally speaking over the last 30 years or so. We've seen snow cover extend decrease in the Northern Hemisphere since the 1970s, especially in the springtime. The snow depth has also decreased, basically really, really strong trends of that in North America and a little bit more uncertain in Europe and Asia. Temperatures rise, snowfall amounts are decreasing, even as precipitation totals may increase. That classic story we just told earlier with Indiana and Ohio, that even though you're getting more precipitation than normal, it's too warm for it to fall as snow. And warming can really lead to an increase in precipitation, but also a reduction in the time period of snowfall accumulation. You're shortening the season for where there can potentially be snowfall. You're basically giving yourself less of a chance for snow to fall. In fact, here's just some evidence of that. This is taking a look at spring snow cover across North America. This is basically the April and June difference from average. And you can see that it's been below average. You should take a look at this for the last 15 years or so, or even more than that. And you can certainly see the trend is downward there. The spring thaw is happening earlier. All of those purple areas along the edges of that white is basically saying when your when your spring thaw is occurring. So what this is saying is that in some places you're seeing that thaw occur. This is with 1 degree Celsius of warming. You would see that potentially that spring thaw happen up to 20 days or more earlier than you'd expect. This could have massive ramifications for the ecosystems in the Northwest because river flooding is a huge issue. If you actually do have snowpack and it warms up earlier in spring and all of that snow melts, you can lead to river flooding. It also leads to there being issues in the summertime. If the snow melts earlier, there's less moisture in the summertime necessarily in case it evaporates, which can lead to there being drought issues as well. So lots of things can happen if you melt snow earlier than you otherwise would in the springtime. And of course, skiing. If you're into recreational skiing, you'll see a smaller ski season. This is by 2050, looking at even a scenario where we take actions to reduce emissions of greenhouse gases. This is not like a crazy high scenario of greenhouse gas emissions. It's actually a scenario where we take a lot of action. You'll still see a pretty significant decrease in ski season times for places across pretty much the entire country, especially across the Northeast and the Great Lakes as well. So I will stop there. And I will gladly take any questions that you all have. I'm sure you have some. And I'm also willing to talk about anything else you want to talk about. Here's your chance to talk to a meteorologist. Ask away.
Okay, well, thank you, Tom. I love your enthusiasm for the topic. Obviously, you have a real passion for this, and it makes it really fun to listen and learn about. So, let's see. We have a few questions. This is kind of going back to these first couple came in from the beginning of the presentation. Someone wants to know what's the best way to observe the shapes of the snowflakes without any special equipment?
Good question. So sometimes, honestly, it's as easy as going out, depending on the type of snow. If you have really powdery snow falling, it doesn't mean it doesn't stick together. If it's wetter snow, it tends to clump, and it makes it really difficult to be able to isolate certain crystals. If it's dry snow, which is it's a really weird thing to say, dry snow, it's water. But if it happens in a cold, it can be powdery. You can actually sometimes just put your hand out there, put it on a black anything that's dark to help the white pop out, and you can tend to see snowflakes. If you have a magnifying glass, you can even see it on that level, at least on a kind of a base level. Otherwise, it's probably best to you need at least a microscope, but you wouldn't need a fancy microscope for this sort of thing to be able to look at just your run-of-the-mill. Heck, sure, they have kids microscopes to be able to take a look at it.
Okay. Let's see. Someone wants to know if the Earth was a little off its axis or orbit, would all these snowstorms all happen the same way?
What an interesting question. So the Earth is actually okay. Here's some cool stuff. All right, why do we have seasons? I'm going to get to the point. We have seasons because the Earth is actually tilted towards the sun. It's actually tilted in space, so it's not rotating like this. We're not rotating like as a straight line, like up and down. The Earth is actually at a tilt, so it rotates at a tilt. So at certain times of the year, the northern hemisphere is tilted towards the sun, and times of the year we're tilted away from the sun. When we're tilted away from the sun, it's winter. When we're tilted towards the sun, it's summertime. We're actually closest to the sun in winter, but it's cold because we're tilted the opposite way from the sun. So that tilt changes over 40,000 years. The amount of tilt changes. So we actually have seen this in geologic past where if you tilt more like this, the planet warms. Or if you go like this, you get more extremes between the seasons. So when you change the tilt of the axis of the Earth, it could actually lead to there being different sorts of ways that Earth regulates heat, and that can change the way climate works on the planet. The ice ages are a really good example of that. I think the snowstorms of the ice ages are probably a little bit different than they are now. And the reason why the ice ages happened was that the Earth's tilt was different. The Earth's orbit around the sun was changed. Sometimes it's an oval, and sometimes it's more circular. That leads to there being changes. And Earth wobbles in space. It's like this. And the wobble can change. All of those things can basically change the amount of energy Earth receives from the sun, and it changes the way that climate works on our planet, and it changes the way storms can form. In the ice ages, you wouldn't have lake effect snow, right? Because the ice sheets may have been over the Great Lakes at that individual time. You also could have seen things like in the Great Lake, if the ice sheets, if it's like Antarctica, because it's ice, it's relatively flat. There's not a lot of friction. You can see storms and winds get really, really, really strong across those areas, which is what you see in Antarctica now when you can see these unbelievably strong winds blowing continuously because of just those factors.
Okay. Someone wants to know, they said earlier this winter, the temperature was reading 30 degrees outside, but it was raining. I guess not snowing. So how can it, I guess, should we assume that if it's below 32, that it should be in the shape of snow instead of rain? I don't know.
Oh, that's another really good question. You can have rain below 32 degrees Fahrenheit, and you can have snow above 32 degrees Fahrenheit. I've seen it snow when it was 38 degrees outside. Why? It depends on the layer of that. How big is the layer of that air that is below 32 or above 32? So in that case, if it rained and it was 30 degrees, that area of 30 degrees might be really shallow. It might literally just be hugging the ground where you are. So you're experiencing 30 degrees, but it's actually necessarily, it's warmer higher up. So as it's above 32 higher up. So as it may start as snow, it may melt when it's above 32 degrees Fahrenheit, and then it doesn't have enough time to refreeze before it hits you on the ground. So it could be 30 degrees and you're getting hit with rain. On the flip side, you could have cases where it's warmer than average at the ground, 38 degrees, right? And the snow, it's so small of an area, it might be colder aloft. And as the snow falls, it doesn't have time enough to freeze, to melt before it hits you. So you can have these sorts of things. It all depends on how the atmosphere is set up. And that's really storm dependent. It can be different each time.
So would that address the same issue? Someone's asking about hail. So how is that kind of referring to what you just talked about, or can you tell us about hail?
So sure. So hail forms in severe storms in the springtime, fall. I guess technically nowadays I've seen them happen in the wintertime, but it's not the same process as snow. So what hail is basically these giant cumulonimbus thunderstorms, those giant towers you see. And basically, the bigger the cloud up in the atmosphere, it just shows how fast the air is moving up. What ends up happening is that ice is forming, and the cloud has enough air that's moving up. So as the ice forms, it gets heavier in like an ice ball. It gets picked up by wind or upward motion, and it gets flung back up in the cloud. And it comes back down and goes back up again. It goes back down and comes back up again, depending on how strong the storm is. And it only stops doing that process until it gets heavy enough to fall out of the cloud. So if you actually cut a hailstone in half, you can see like layers. And that's basically each time this hailstorm kind of like traversed the cloud because it's gotten another round of liquid water to freeze on it. So it's a little bit different of a process um, than a snow crystal forming like a snowflake.
So someone wants to know, do you get the same types of snowflakes falling in the same place at the same moment, or could you get different kinds of snowflakes mixed together?
You can get different sorts of snowflakes mixed together. Now, if they're forming in the same area, they're probably going to be generally the same shape, but they're not going to be exactly the same because they're going to be different microclimates going through them. But because what I've been talking earlier, the temperature differences can be different. That this part of the cloud, snow might be forming in a different shape than this part of the cloud,
Hmm.
and they might fall at different speeds. So by the time they reach you, you might see different sorts of things fall, you might see them, and oftentimes you'll see them sometimes stuck together. You can see these different shapes stuck together. So it's also entirely possible because it all depends on just the temperature within the cloud, and it's something frankly that we can't measure while the storm is happening to like an unbelievable amount. So we can't like give you snow crystal forecasts in general because we're talking these differences can be very, very minute in the cloud.
Let's see, someone else wrote, because I love snow too. If anyone is interested in crystals, I recommend W.A. Bentley's Snowflakes and Photographs. Um,
Agreed.
you're nodding your head, yeah.
Two thumbs up. Really good. Check those out. They're beautiful.
And then the same person's asking about colored snow.
Colored snow.
Do you know anything about that?
Um, I mean, the reason why, I mean, it kind of goes into like sunsets, blue skies, the same reason why our eyes perceive things being a different color. It all depends on how the light is scattered.
Hmm.
So I can imagine like blue snow. For instance, it could just depending on like the angle of the way light is interacting with the snow itself or the ice can lead to your eyes perceiving it as blue. So there's ways of doing that. Um, Yellow snow, don't eat the yellow snow because we all know what that's about. I think that's probably the reason why you see it. It's why we see sunsets. It's why sometimes the sky can look green during really severe storms because the sun rays are getting bounced off everywhere and our eyes perceive it as green. That's probably the reason behind it. Otherwise, the eyes, people are just putting stuff in.
Yeah,
I
Tom,
think that might be.
there was a story like last week that it was kind of like on like social media that like Reese Witherspoon did this thing with snow where she went out into her backyard and she got snow and she made this drink in her kitchen with like I don't know like heavy whipping cream and things like that. And some people were like freaking out that she was actually eating the snow. And I guess like is it really safe to eat snow if it's not if it's like if it appears clean, if it appears untampered, is it okay to eat snow?
Um, I saw this. It was like snow cream. I'd never
Yeah.
seen anyone ever do this before in my life, but apparently
Okay.
it's a thing that people do, and I
Yeah.
had no concept of it. Um, I mean, as a kid, I ate snow. I'm fine.
Yeah.
But I probably wouldn't because I
Yeah.
don't know. I don't know what. I mean, the nuclei are dust. It could be dirt. And it's also falling on the ground. Maybe if it just fell, it's on the top of stuff. Maybe it's not that bad. But if I'm going out after a storm and that snow has just been sitting on, um, like a picnic table or like a chair, I wouldn't grab that because there are animals out there also living. And they can be walking
Yeah.
through these things and other things. But I mean, I'm sure if you douse anything in cream, it's going to taste good. So,
Yeah. Okay. Right. Okay. Well, I drove through Lake Effect Snow last week in southwestern Michigan. I'm actually about to do that same drive tomorrow. I'm nervous about it, and especially when you said that you can have lake effect snow even in the upper 30s. So I'm hoping tomorrow I have a good drive because I'm literally driving that route tomorrow, and I'm hoping I don't encounter the same thing I encountered a couple weeks ago. But yeah. Let's see. Someone wrote, I saw the aurora borealis in Norway last year. To our eyes, it looked white. On our phone, it looked green.
huh,
Why is this?
I don't know. That's cool, but also you've lived my dream. That's like the one thing I want to see in the world is I want to see an aurora borealis. Um, that's interesting. I wonder if it's because the shutter speed on the camera was longer than your eyes, so it allows it to pick up different colors. Um, that could be that maybe it's because the was open because you're trying to capture it. Maybe that's why. Um, Otherwise, I don't know why. That would be the
Oh,
case.
the same person said she went to Tromsø, Norway. So that's what she recommends. Okay. All right. Well, I think we got through most of the questions. Some of the questions kind of overlap some of the material that you covered during your presentation. So I just really want to thank you for this presentation. What other topics do you talk about? Like what besides snow?
Oh, I talk about everything. I talk about hurricanes, tornadoes. I'll talk about just generalized climate, climate change. No matter what
Uh-huh.
it is, I usually talk about El, if you guys have heard of El Nino before,
Hmm.
I'm one of the federal forecasters of El Nino. I'm one of the like 10 of us who declare it being here. So if you ever get sick of El Nino being bandied about, I guess I'm part of the reason why. Because we declared it. So, but I'll talk about it's the atmosphere is so neat. There's so many different cool things to be able to take a look at, and things are changing so much that um, it's important that we all kind of talk about it.
Did you ever think about going pursuing a different career, like working as like, working on TV and doing like weather forecasting in that format? You took a different path. So I'm just curious.
Sure, yeah. So I initially, when I went to college to study this, I thought I was going to be a TV meteorologist.
Hmm.
And then I tried out in college, and I found out I'm not very good at pointing at things backwards. Just not good at that sort of that sort of like show sort of time. I'm much better like this, and it's fine. Um, but the one thing that was consistent, I realized afterwards, is I like the aspect of helping people. I like making sure that people had information to make the right decisions. And that's like the core of why I became a meteorologist. So um, I kind of got more into climate, and that's where I am now. Now I get to do more communication work, which is what I really, really like to do. and I always find it a fun. I've always been a big fan of puzzles, and there's no better puzzle than trying to figure out a way of communicating this complex topic. So it's like every day I get to do a new puzzle, and the weather's great because I have a short attention span, and the weather changes every day, so I always have something new to talk about.
Right. Okay, well, we have some nice comments coming in just saying that they thought it was a great presentation and thank you very much. So I'm just going to say thank you to you, Tom, for joining us tonight. And I know it's getting late on the East Coast. And thanks to everyone for joining us at home. And we hope you enjoy the program tonight. So have a good
Right?
night, everybody.
Good night, everybody.
Bye bye.